As I said, sometimes they don't give you the diagram, and what if you have information here, and you're looking for the probability of A sub I given that E has occurred, where A, 1, 2, 3, all the way through N is a partition of a sample space, so these are going to be mutually exclusive groupings in a sample space, with E an event that can occur across all of these other partitions, all these other sub-events of sample space S. If I want to do the probability of A, any one of those A's given E, what I would have to do is first figure out what the probability of A in general is, times the probability of E given A, which is often something that's a little easier done. And then I would have to take each one of those sub-probabilities, probability of A1 times the probability of E given A1 plus the probability of A2 times the probability of E given that A2 has occurred. One of those probabilities are going to be the same as what you have on top there. So whatever I represents, if it's like the third split, the fourth split, it's going to be both in the top and bottom as part of an addition problem. So for instance, how will we make use of that? If a certain disease is present, then a blood test will reveal it 95% of the time. But the test will also indicate the presence of the disease 2% of the time when in fact the person is free of disease. If 0.3% of the general population actually has the disease, what is the probability that a person chosen at random from the population has the disease, given that he or she tested positive? So in this particular problem, before I get you started on this, let's kind of wrap some things up here. I'm going to let the plus sign mean that I tested positive, and I'm going to let D stand for having the disease. So what we're looking for here is the probability of D given that I have a disease, given that I did test positive. If you look at the information that you're given, as I'm going to show you really quick, the information that we're given is that, okay, well, the green one, if the disease is present, so I'm given that the disease is present, I have the disease, of getting a positive blood test is 0.95. So that's the probability of positive given that I'm diseased. Notice it's not the same thing as the probability of me having the disease given that I tested positive. I want to know, what that probability is, because that's important to me, because if I took a test and it tested positive for the disease, I want to know what the likelihood is that I actually do have it. In blue, we're given that the probability of being positive given that I don't have the disease is 2%. And of course, the probability of me having the disease is 0.003. So that's the information that we have. If you do this the correct way, for this one I'm just going to use the formula. So according to Bayes' theorem's formula, well, there's some information I'm going to need to know. So I'm going to find some additional information that's pretty easy to have based on the numbers I already got. If the probability of me testing positive given that I have the disease is 0.95, then the probability of me not testing positive given I have the disease is 0.05. That stands to reason. The probability of me testing positive given I don't have the disease is 0.02, which means the probability of me not testing positive if I don't have the disease is 0.98. And then, of course, the probability of, since the probability of me having the disease is 0.003, the probability of me not having the disease is 0.997. Because some of these are going to be needed as I go through Bayes' theorem. Because if I'm going to do the probability of D given plus, then I'm going to do the probability of D times the probability of positive given D, which I had, over, well, that product again, the probability of D times the probability of positive given D, plus the probability of not D times the probability of positive given not D. So I had to figure out these things more so, and what's most importantly, because I needed this probability right here. Without that, no, sorry, not that one. But they gave us all the probabilities, actually. Just wanted to make sure I had them all. Well, no, I needed this probability down here. That's the one. I circled the wrong one. That's why. I needed that probability. I needed to figure out that probability in particular in order for me to be able to come up with the calculations I needed. Depending on what other kind of options there are, you may have several options down there, as what's indicated in the formula. So if I substitute these values in now, on top I have 0.003 times 0.95. On the bottom I have 0.003 times 0.95 plus 0.997 times 0.02. And when that's all said and done, and I calculate it, I get about 0.1251. So the probability of me actually having this disease, given that I tested positive, is about 12.5%. So, you know, that could be a sigh of relief, or that means that you may have to go through more testing, you know, before you get over concerned about it.